if you have strong interest in any problem, you can get some data from that field and form your own problem, even very innovative stress problem formulation, and then you may be the one to provide really valuable suggestions to the field through optimization techniques. Okay, so that is some topics for you to consider for your individual projects. But realize that NBA is very fun, but you can also focus more on your research and engineering relevant problem. That's even more important. Okay, so this is what we discussed about the class requirements and some examples. Now let's move back again to the basic formulation of the optimization problem. So we look at the structure of optimization already with the objective function. Here we just use x, y to indicate the process variables, z to be the objective function for cost, for we can minimize the cost, minimize the environment impacts, subject to the model constraints of the equations describing the process, such as energy and materials balance, and inequality constraints, such as the process requirement, safety constraints, and your variables can be continuous to be the continuous variables or the discrete variables, binary variables, to be the logic decisions. This is what we have seen as a basic structure. But when we form the problem formulation for a specific type of question, we will be able to understand more how to use this framework. Okay, so the standard form of a continuous optimization problem, let's start with the continuous first, is to minimize or maximize. As we say, maximize is just to minimize its negative value. So it's the same. So we just use minimize its objective function. It can be a function of f, or you can write it as multi-objectives. So if you have multiple objective function f, you want to minimize every one of that, but those objective functions will have competing values possibly. So we'll discuss multi-objective or single objective. And your goal is to get the value for your variables, optimization variables, x1 to xn, and subject to inequality constraints and equality constraints listed here. So use a series of functions to indicate that. Okay, so note here we use I, but actually these numbers can be different. So it's better to use the value of j, right? So it means depending on how many constraints you can have a series of equations and a series of inequalities. And then optimal solution is variable x, use x star here. That gives the smallest value of f0 among all vectors that satisfy the constraints. So this all the vectors of x that satisfies the constraints, we call it like a feasible region. So among the feasible region, all constraints are satisfied. So any points within this region will be feasible solutions. But because it's continuous, you are not able to evaluate every point within this. It's infinite. So the strategies to solve the optimization is to give you the f value among the feasible region to give the smallest value of f. So that is the way how we solve the optimization problem. With this structure, we can again look at some examples to see how to use this structure. Let's start with a business application. It's maybe relevant to your background if you do some personal investment, or you buy some stocks, or just simply you got $100 to spend in the supermarket, in a mall. You want to get a basket of products, stocks. So we call this kind of problem a portfolio management and optimization. Then consider the variables for this problem. What is your x? When you got this total money, your goal is to make investments. So the amount of investments in different type of assets will become your decision variable x. So if you have all type of options, you can invest xi to the each type of investment to be your decision variables. So the objective in this case will be like the total value or total the money you can obtain, the profits. But commonly used in finance, they also use an objective to be the overall risk of the portfolio or return variance. So these are different formulation of the objectives. If you learn a business class, you'll know how to quantify this risk. But then if we just have the objective here, it can be one goal to obtain. Well, the constraints for this problem can be the total budget, the maximum or minimum investment per asset. You have to, sometimes when you buy one product, you have to, the minimum number you have to buy, maybe they give a bundle, those things. And in this case, the minimum returns is put as a constraint. So if you have no finance background, this example may be quite difficult. But this is not the single formulation for portfolio management. If you are like a risk, you don't care about risk, because in financial industry, they want to minimize the overall risk. But if you don't mind the risk, you just want to get the returns, you can also put your total returns as the objective function. So it's a lot of flexibility there. If you want to get your returns or your revenue from all the portfolio to be maximized, you can also form this problem, the objective as minimize if we want to maximize the return, it's the same as minimize the minus of the return, right? So you can also formulate this and put the risk as a constraint, right? Because the risk, then if you still want to manage a reasonable portfolio, you always have the risk criteria considered. It can be a total risk has to be smaller than certain value. So this is a commonly used financial example. Well, we also have many different kinds of examples, especially in our industry or supply chain applications. The second example I want to introduce to you is a data fitting example. This one you must have used that before, although you did not realize this can be regarded as a typical optimization problem. In statistics or machine learning, you want to get some model to describe the data. It always got a data fitting problem. So here, think about if you got several data set points and you want to form a function to describe it. Then these function parameters, this A, B, C, D parameters in your function or in your model will become the variables here in your optimization. So you got the optimization variable to be the model parameters in your data fitting problem. And then the objective is that we want to make the misfit or the mismatch between the model and the data, real data, to be minimized. Or we can call it prediction error, because you want to minimize the error of the real data and the model, right? And this error has different way of calculation. You can use direct absolute value or relative value of the error, or kind of the evaluation of the measurement. Well, this model can be formed in this way, or it can also, in this way, it's unconstrained. The goal is just to minimize those mismatch between your model and data. But because now we have the optimization tool, we are also able to add some constraints to the model. Right? Like if you say we got some prior information about my model, if I know some of the model parameters must be positive, its correlation, the slope must be a positive slope, so it's our non-negative values, you can add those as constraints. Or if you know some parameters must be within certain range, then these constraints can be added to the model. Okay, so this is some examples we give you using this optimization formulation. You can take the time to think about what is your own problem you want to solve, following the initial steps to form the problem like this. Using this framework, you can think about your own problem formulation. So take 1 minute to write down your problem objective, your variables, and some constraints for your problem. Now you can click the pause and start to even think about what you will do for your individual project. At this stage, you don't have to know exactly how to solve it, but any problem that you have seen in your research, in your other classes, or in your daily life, in your family investment, you can write it down. Try to solve that using optimization later. After you successfully defined your problem and formulated it as the structure of optimization, we will learn how to solve this optimization as the final output from this module. Those general real-world optimization problems are normally quite difficult to solve, constrained by the computational time, and sometimes it's also not able to find the global optimal solutions. So again, think about the problem of we climb a mountain. If the mountain is clearly, we got know this peak some point and it's all through the very smooth ways, it's eventually feasible to find the peak. But sometimes it's quite difficult. The slopes are very challenging to give you a mountain like that. You won't know the peak is somewhere located here. You might get stuck along the way and think this is a final point and stop to try to find the global optimum. So these are the solving strategies that still remain unsolved in the real world large scale problem formulation and solving. Therefore, we will study a lot of techniques, the most commonly used techniques we are able to solve. But beyond these difficult problems, there are some formulation strategies. We have some exceptional good cases that have been well studied and suggested with very good solvers and algorithms to get the optimal solutions. So some examples, the least square problem. What is the least square problem? If you do the data fitting, you might have learned you have got some error, right? And the error square, you want to minimize it. So it's a least square problem. Or the linear programming to form it as a straight line, as a linear function. It means both the constraint and objectives are linear. Or more broadly, convex optimization. So this concept we will introduce. What is convex? But remember that those type of problems are very good to be solved efficiently and reliably. Okay, so if I tell you for some data fitting, I got 10 million of data points and I want to get a linear fitting to that. You may think, wow, the data amount is so large, it may take forever to solve that. But think about how long will a computer take to solve a linear programming, or for example, to solve the next case we will discuss, the least square. Least squares problem is a very commonly seen and used problem in many different disciplines whenever you have data. So the standard format of a linear squares problem is listed as minimizing this square format objective function. So this is a linear format using a matrix formulation, and this is a square of the arrow term. So don't be worried about getting exact understanding of this. Let's do this step by step. But this least square problem is so widely exploited that many standard techniques can solve the problem very efficiently. So as we discussed, we just asked how long will it take to solve like a least square data fitting problem with 10 million data points. That can be within milliseconds if the computer is effective. Because this strategy to solve it is very mature. So analytic solution. If you learned well about matrix operation, linear algebra before, you will be able to solve this objective function, this second order square term, to get the minimization. If you know the for this problem, the convex problem, the extreme point corresponding to optimal solution equals to dy over dx. Make the first order derivative to be 0, and it gives you this analytic solution for the optimization, where A is a matrix before your variable and B is another parameter. Okay, so standard techniques can increase flexibility of the least square problem. Like if you have different weights on the series of the points, you can emphasize certain points more, or you can add some different regularization terms to pre-process your data. We will talk more about this later. So what does a least squares mean? If you look at a simple example, here we have 4 data points collected, very simple, just 4 points, and you can easily write it down. So it's a 2-dimension, only x and y value. You got your 4 points to be 1, 6, 2, 5, 3, 7, 4, 10 labeled here, and you want to get a straight line to fit this data. This can be your experiment to measure data, or can be some correlations. Can be the any correlation like the height and the weight correspondence, or the time and temperature. So any of these relationship between data, you can capture it first, get a look of the data trend, and then fit the curve using our least squares strategy. So here the curve, the line is simple. It's a straight line, so it's only 2 model parameters. But recall that when we see the data fitting problem, the model parameters for your model here, bit 1 and bit 2. When you formulate this optimization, the objective becomes the fitting arrow, as we labeled here. Well, this beta parameter becomes the variable in optimization, which means the value of these parameters are varying until we find an optimal point where the S value, objective function value, is minimized. So here our goal is to vary the parameter value of beta to find the corresponding minimize the value of the fitting arrow S. Okay, so this is the least square problem. So the arrow is written as a way to be the mismatch or misfit between the data point and the fitted value with a square term. Okay, so this is the standard way how we write the least square problem. Here only 4 data points, so you can easily write real y value minus the model returned y value, and the arrow is squared. Why do we use the square? So think about, you can write down the absolute value, right? So 6 minus this beta 1 plus 1 multiplied by beta 2. So this is the absolute value, but it can be positive or can be negative. You want to minimize all those arrows in both directions. Therefore, this square term can be used to make it always a positive value, and then you minimize the summation of the squares. To make it positive, you can also directly use the absolute value, right? So it's also sometimes called absolute arrow. But the feature of absolute value is that the problem will not be convex. So we will introduce you the concept of convex later. You know, by direct sense, a convex means kind of like this kind of curve. If it's absolute, it may be disconnected at a certain point. In this way, the function is difficult to use the standard strategies. Therefore, the least square problem has its broad application in the field. Okay, so because only 4 points here, so we only have 4 arrow terms to sum up. You can have more if your data points is a large scale or millions of data points, doesn't matter, but the arrow function is written in the same way. And now is the question, how do we get the value for beta? For this convex problem, we know that when the point is at certain point, the first order derivative is equal to 0. This can be a minimum point. It can be a local minimum or global minimum when it's a convex problem. This is also a key concept we are introducing in the class later. But here we know we just make the first order derivative from s ds over d beta 1 ds over d beta 2, make both terms to be 0, and force the value to be 0 to solve for this beta 1 and beta 2, and we are able to get just from these 2 equations 2 variables. We solve beta 1 is 3.5, beta 2 is 1.4, it's easy calculation, and then we fit this curve here. So this is a simple case how we use least squares to fit a straight line. When you have more data, the strategies are the same. And this is very useful in many disciplines for optimization problem. So here the key thing is optimization, minimizing the fitting arrow. This type of formulation has broad applications in data fitting, as nowadays we see data is a new currency. Whenever you got data, you're able to make a lot of analysis through the statistics, machine learning methods. Again, we call that the variables here in the optimization setup is your model parameters, and objective is to make the prediction errors minimized. Also, we realize this type of problem, we have no constraints. So it's unconstrained optimization. It's easy to solve. We can directly use the first order derivative. When we got constraints, we need to do more operations. So this type of problem has abundant applications for classification, data fitting, regression, etc. Right? So least square problems, remember that. Then the second broad type of case studies Wang introduced to you is linear programming. We will have 2 or 3 classes focusing on the linear programming in the later part, but I'll give you a general sense. What is linear programming? So the standard format, you see you have the parameters, you have the coefficients before your variables x. So this C can be a matrix corresponding to a dimension of your x, of your variables, well subject to a series of constraints. Both equations are inequalities, that's possible. But all the objective function and the constraints are linear functions. You have learned the term of linear. So it's a straight line in the 2D dimensions and even higher dimensions. It's linear combination. So this type of problem is first proposed by Danzig in 1974. So the history, think about it, it's not that long. You only got less than 100 years of development, but they have seen so many promising applications. It's basically the way to do programming in the linear structure. However, the problem for this type of problem, there is no analytic formula for solutions, not like the least square. You are able to use your hand by calculating the results. When it with constraints, you need to combine this with either some graphs to get the simple solutions to the corresponding to this constraint space, feasible space to get objective function, or you need to use numeric simulator computer to get optimal results. But it's also material technology. We have widely studied linear programming to find its optimal solutions. To use linear programming, there are some standard tricks or algorithm to solve the problem, and also to put many different problems into the linear structure. So we will show you how to model some problem in linear structure later. And beyond linear programming, we will also talk about convex optimization. What does convex mean? So this is a new concept to most of us. It's in optimization field. We define a convex optimization that has objective, the same way the constraints, but all objective and constraint functions are convex, which means for the function f, let's again use some figure to show that. If we got 2 points, x1 and x2, and then the combination of x1 plus beta x2, where f plus beta equals 1. So for example, 0.5 x1 plus 0.5 x2, or 0.2 x1 plus 0.8 x2. What does this mean? So this is a linear programming of linear combination of x1 and x2. When you write this of x1 plus beta x2, it means all the points on this straight line connecting x1 and x2. So it is this line. All the points on this line, if it's x, so draw your x and the y. So the corresponding value of those x are laying on this function, right? So all the function value are here. It means this function value corresponding to these points in between are smaller or equal to of f x1 plus bit f x2. What does this mean? Again, it means the f value. So this is your y-axis. It gives you a function value of f. The combination of f x1 and f x2. The combination of fx1 and fx2 weighted by alpha and beta lay on this curve, and the f value of this x theta in between are the function value here. So if the function value of alpha x1 plus beta x2 is always small or equal to the combination of the two function value f, so we compare these two curves basically each point, it means this is a convex function. Alright, so this is a typical convex curve, looks like this. A more detailed definition will be given, but this is in next lecture. This is the basic concept, you remember. This is a definition of convex. Whenever we determine whether a function is convex or not, we go to the criteria to see. Here, alpha, beta are both positive, non-negative numbers, so they in between 0 to 1. Okay. Their linear combination makes the criteria to compare. So corresponding, the opposite to convex is what is concave. So concave, if you think about what is the definition of concave, think about it. It will be introduced next lecture. But for convex optimization, it is easier to be solved, although it's also no analytic form for solutions. But we can have convex optimization strategies to effectively solve many of the problems. But for concave, we then need to convert that to convex. It also continues. If it's not continuous, we can get some break the complex problem to parts to make it easier to solve. Okay, so convex optimization is also a concept we will emphasize and use some techniques to solve it.